Okay, thanks everyone for coming. So it's my pleasure today to introduce our speaker, Professor Irfan Siddiqi. Irfan is a professor of physics at the University of California at Berkeley. Initially as a postdoctoral scientist, and then in his group, Irfan developed a lot of the techniques that have become ubiquitous for measuring and characterizing microwave radiation at sort of the quantum limits. And his group's also been very open with their research. So, for example, we have amplifiers in our fridge that were developed by Irfan's group in collaboration with Lincoln Labs, and so we appreciate the hundreds of hours that we've saved. A lot less coffee gets you drank because the measurements finish more quickly. But he's also won all sorts of awards, the DARPA and Air Force and Navy, all the Young Investigator Awards. Okay, so please round of applause.
Thanks. Thank you for the kind introduction and kind invitation, and also thank you to Monica, who is not here, for also extending the invitation. Can everyone hear in the back? Okay. So I am an experimentalist, so I build things. So I don't ascribe to any particular theories except the ones that I can measure. And that's a little bit of the spirit of the talk, saying that there's something really interesting happening in my field. And that is, we have gone beyond asking the question, can circuits be quantum mechanical? Can big things be quantum mechanical? To agreeing that they are, to asking another set of more sophisticated questions. What happens to quantum mechanics in the limit of complexity? So on and so forth. So I've given the title, The Dawn of Superconducting Quantum Processors, saying that we've gone beyond, as a community, the idea of simply building a one-off or two-off circuit that behaves like an atom. We're asking a new set of questions. And in particular, the talk sort of goes back and forth between basic physics and perhaps what one could do in the domain of quantum information science. But I don't ascribe or unascribe to quantum computing. And in particular, I'm curious to see, as a poll in the audience, how many of you think we'll have a quantum computer in 10 years?
What do you mean?
Anything you like. How many of you think that quantum computing will never work is total rubbish? It may be. It may be. But I think what I want to get across to you is we have a new set of experimental tools. And we probably don't know the right questions to ask, and we don't know the right applications. But for an experimentalist, that means great, we have more work to get done. So I'd like to start by thanking some snapshot of the group. This is my group on campus. We have another group at LBL. It's all seamless. We're going to sort of be about 30 to 40 people soon enough, but I don't have a picture of that to show you. But nonetheless, these are the folks that are doing the hard work. Okay, this is a snapshot of what I'm trying to do today. I may not get to all of it in the same level of detail, but I will spend a little bit more time in the beginning here talking about, well, what's really different about quantum? What could you possibly do in this domain, given what we know now? What is the technology like? How do you actually go on to things that have more than a few quantum elements? What are some applications that we see? And in particular, how to advance the field in a more collaborative kind of effort. That's the snapshot of the program for today. So let me talk about the quantum world around us. It's absolutely no shock to us that quantum mechanics is everywhere. And quantum mechanics is the law of the land under the hood. And we have used those properties for all the things we're familiar with in our daily lives. So I was having shoulder pain when I was writing this talk, so I thought it would be good to talk about an image of it taken by an MRI scanner. And in particular, one can look at the quantum mechanics of water molecules, in particular protons that are there. And these have spins, right, that you can polarize with a magnetic field. And the critical thing to note is that once you've chosen a measurement direction, then you've chosen an output of your measurement. The spin will be aligned or anti-aligned. You could prepare that spin in a more complicated state, let's say a superposition in green here. And if you were to measure this, shown here in the block sphere, where your measurement will only yield 0 or 1, you would, of course, measure 50% up or 50% down. The critical part, of course, is that we are not doing MRI on a single water molecule. Right? You have a chunk of matter, and you are looking at some emergent or collective phenomenon. Okay? And that's the type of interaction that we've been used to in materials, in MRI, and all sorts of other quantum phenomena. Okay? So the take home here is that quantum systems can exist in many different configurations, even if you can't observe all of them. So there's a lot of complexity under the hood, and the real question is, how do we actually get access to that complexity? So let's try to build a quantum computer, as people did in the old days, one molecule at a time, a la NMR. So I can imagine a system where, unlike MRI, which measures average properties of a group of spins, we need to address each spin individually. I could put them on a lattice. Okay. This is assuming I can measure all of them. Okay. Let's just take this particular fellow here. You can give him or her a name if you like to make it more personal. But this is red spin. And your measurement reveals red spin to be up. Okay. If I cover up red spin, and I don't know the state there, the most general representation that I have is some combination of up and down written with the coefficients A and B. Everybody okay with that? That's the most general state of this particular spin. Let's imagine the neighbor here, written also as a set of numbers, C and D. Okay. I can think of coupling adjacent pairs. So now I interact these two spins. And I can look at a set of states which are simply tensor products or products of these states, like this. And you will get some combination of both of them being up, one of them being up, one of them being down, one of them being down, the other one being up, or both of them being down with the product of these coefficients. Okay. It would be wrong to think that those were the only possible states you can get in this system. Okay, because this particular representation ignores this very simple state, up, up, plus down, down. And you can see that because there's no set of numbers, A, B, C, and D, that will give you this particular state. Okay. So in particular, you can imagine trying to cancel this term, one of the terms, by setting A equal to 0, but then you lose this part. Or if you set D equal to 0, then you lose this part. So very easily you can see that the manifold of states that are possible are much larger. And in particular, these type of entangled states, if you like, increase with 2 to the n in terms of their complexity. Okay. And 2 to the n is much larger than simply 2 times n, the number of classical combinations that you can get. So this is sort of in a very simple example telling you the complexity that you can have in a piece of quantum matter that's fully entangled. Everybody okay with this? Okay. What do you do with this entanglement? That's a different story. We will talk about that in the rest of the talk. I can't resist being at least a slight salesperson here, saying that if you really had 300 such entangled elements, you would need more numbers than the particles in the universe to describe that array. I have now said my salesperson pitch. Okay. What's different in this flavor of quantum science than other flavors of quantum science, such as the science of quantum materials, so on and so forth? If you imagine nature having quantum structures that are there, how does nature preserve these quantum effects? Well, as a quantum material scientist, and I apologize to all real quantum material scientists, a faux scientist like myself trying to put together quantum materials thinks of this endeavor as simply assisting or encouraging nature to assemble extremely complex structures. Nature is actually doing the assembly. We may have the little puppet strings to pull on. And in particular, nature has pathways to preserve quantum coherence by a structural perfection and symmetry. No defects, 2 layers, very complicated, beautiful geometries, so on and so forth. And at the end of the day, as engineers, we use the emergent phenomenon that comes out. What's the bulk resistance, the bulk transport properties, the capacitance, so on and so forth. If you're trying to engineer a chip for quantum information science, life is a bit different, because in fact, we need to complete the design and synthesis of the matter from step 0. We don't know the lattice structure for making our array of qubits or a quantum computer. We have to think about where those linkages will be. Okay, and we don't get it right. It's an evolving process. We also have to think about getting information in and out. So there necessarily will be surfaces and interfaces and ports. And that's hard with quantum mechanics, because you can perturb the information that's there. The one thing that keeps us alive, Bob, is that even though we put in these ports, we can read out information from these ports. So there is a possibility to control the system in ways that we haven't done before. But if you don't use that information and read it out, then you lose your advantage. Okay. So in a nutshell, just trying to specify some of the challenges with trying to build a system which is truly quantum mechanical at the individual quantum level. This can be done in a number of different platforms. We can imagine using actual systems that have intrinsic quantum behavior, like spin or charge. So one can imagine trapping individual charges in silicon hosts or diamonds, or trapping individual ions, or actually using photons themselves. You have companies very close by in the neighborhood that do this. Or we can think of things that are larger, macroscopic. So today we'll talk about superconducting circuits and how they can mimic atomic behavior at larger scales. And of course, perhaps this would be the holy grail, where one can build in some kind of topology into the circuit to really protect quantum mechanics. This, of course, is a challenging road, and we all look forward to things evolving in this dimension. There's a nice report if you want to catch up on sort of a 10-minute snapshot of QIS put out by the Boston Consulting Group. So this particular, how many of you have seen this report? Okay. But nonetheless, it gives, I think, a reasonably accurate figure of merit, saying like, here are the different approaches. You need to have certain gates and lifetimes and fidelities and all that. And superconducting qubits are doing quite well in terms of a technological maturity. So they are, if you're in the government business, TRL level 5, meaning that you may be able to do something soon. Okay? But nonetheless, it's a nice report to reference, just to get a very broad overview of the field. Okay. So I want to put on a quasi-theorist hat for a moment. So you'll have to forgive me. I had started off as a mathematician, so I'm enjoying coming back a little bit into this. I do want to point out some of the basic ideas of the algorithms that we've been looking at in this space to illustrate why they're hard, right? And in fact, what are the improvements we need to make, okay? So again, from the same report, things that you are hearing about, a lot of possible applications in high tech and machine learning and logistics and so on and so forth. To a mathematician, here are the things that you can perhaps do with these systems. You can look for patterns, take Fourier analyses. You can search a database. You can find the energy minimum of something, and you can do matrix math. And if we were able to do that, we would be able to do a lot of things. Okay. The challenge for that is the lifetime of our qubits is not long enough to allow you to do enough logic gates. Okay? And I'll show you why the logic gate count gets high. Moreover, it's very much unclear what classical resources you will need to interface with your quantum computer. And I will also illustrate that in a slide. So let's start with this. This is perhaps one of the most well-known quantum algorithms, Shor's algorithm. It requires a little bit of heavy lifting to figure out exactly what it does. But in particular, the algorithm that gets the most work done here is this little bullet here, which is hard to read, so let me illustrate with my fingers. This is called phase estimation. Okay? So with phase estimation, you have a vector that points somewhere in space, and you'd like to know its angle. Okay? Classically, you can take its projection. You take a cosine or a sine. The accuracy of that measurement scales as 1 over square root of n. Right? That's just Gaussian scaling on trying to measure classical quantity. If you imagine breaking up phase space into a certain number of angles, let's say 4 angles, cardinal positions here, you can make use of this property that if you have 4 angles separated by 90 degrees, if you apply a 90-degree rotation twice, you will only get 2 outputs, right? Because you end up having 180-degree rotations. So the whole idea of this phase estimation algorithm is to come up with a set of different rotations shown here as these U's, and they will pick off each piece of your phase estimate. So you start off with 1 rotation, and you get the most significant bit. Then you rotate, and you pick off the next significant bit, so on and so forth. So in particular, you take an angle, and you turn it into a bit string that gives you the information about the angle. That's the inverse of a Fourier transform. Right? If you run that circuit in reverse, and you take a set of bit strings and you turn it into its angular representation, that's a Fourier transform. So quantum can do this in not square root of n steps, but 1 over 2 to the n steps. So in fact, you get, because of this quantum projection, an improvement. So that's a hand-wavy, quasi-mathematical way for you to understand that this is sort of an important function that was realized early on. If you can do this Fourier transform, then the business of finding the prime factors of a number, the classical algorithm is basically reduced to period finding. And the period finding step is hard. Apply Fourier transform, problem solved. Kind of. Right? There's a lot of things that need to go on. A lot of gates to run this, a lot of accuracies, encoding, decoding, so on and so forth. Difficult algorithm to run given the state of affairs of current hardware. But it's a good start. It motivates lots of things. You've heard of Grover search. The idea here is a little bit similar but different. You want to search for a certain value of x in the domain and that satisfies a constraint. You make a superposition quantum mechanically of all the states, and you run an algorithm to pick out one spot which is of interest. And all you do is use phase inversion. Right? You change the sign of the little blip, and you subtract the mean. And that causes this little blip to get more prominent over the others. So it's a very good algorithm, runs in square root of, logarithm number of steps rather than the usual polynomial number of steps. But who can guess one of the major difficulties with this? What have I assumed very nonchalantly here? We said we need to make a superposition. That's super hard. You have to read out all the classical entries and make a vector out of that. Right? What is the RAM, if you like, on your computer that holds all those quantum values? Okay, so a lot of these steps can be very tricky in the algorithmic space. Linear algebra, you use phase estimation to figure out your eigenvalues. Okay? So challenges, many gates may require fault tolerance, correcting for errors. You may need a RAM that actually holds on to all of this information. Very hard. Okay? And often have fine print. You can't always solve for the matrices except in limits of sparsity and so on and so forth. Okay? So moreover, this is for our young theorists in the audience, actually how do these algorithms use entanglement, superposition, interference, etc.? It's not obvious. If you look at Shor's algorithm, where's the entanglement? It's not completely obvious. You use entangled states, but it's important for us to manage these resources very carefully going forward, because they're expensive experimentally. Okay. Things that are more near term. Let's not think about machines that can run all of these gates, so on and so forth. Let's think about machines that will only solve very specific problems. Right? You can set up a physical set of qubits to do a simulation task, and they may be rather informative to all sorts of these interesting problems in condensed matter physics or high energy physics. Okay. I also want to sort of end the algorithm part by saying there's actually a lot to learn in classical computing by quantum computing. Right? So in fact, there are examples where quantum computing and quantum ideas have led to better classical algorithms. So this is a very famous problem. This is the Netflix problem, or the Amazon problem. You get a little email that says, a person like you would love to buy X. Okay? And that's based on certain preferences. You've bought Y, Z, and Q in the past, so one tries to create a matrix called the preference matrix and tries to fill in the other entries that are there. Okay? So this is a classic machine learning task that's there. And the funny story is it's actually a very hard task classically, because you'd have to sample a matrix and it goes as polynomial in the dimensions of the matrix, which can get big. So Scott Aronson put out an interesting challenge to this particular paper. This paper came out with a polylog representation saying that you could use quantum mechanics to solve this matrix reconstruction task. And the challenge that Scott Aronson put out, he said, prove that this is the best way to do it. And the student, of course, found a better classical algorithm to solve this problem. So this is interesting. Why did this actually happen? Because the sampling method was very different. So you see, the takeaway I take from this is that there's quantum mechanics and then there's wave physics. Wave physics can be perfectly classical. And if you apply classical wave physics, you can get better classical algorithms. It does not necessarily have to be coherent or entangled. So there's an example. Genetic algorithms have this. Right? People have thought for many years how to cross populations in some quantum-like way to get more diversity. And also with things that are very machine-oriented levels of tasks and optimizers. So I just want to leave that because a lot of people are asking, well, how do you know that these are the only algorithms? Well, we kind of don't. Right? We're sort of figuring out what can perhaps be done in the near term. Okay, so let's go on to superconducting qubits. This is a typical circuit we're used to in some electronics class. How the heck is that quantum? What does that have anything to do with atomic physics, so on and so forth? Well, it has R's, L's, and C's. Okay, so it has resistors, inductors, and capacitors. And you excite these with voltages. And classically, these R's, L's, and C's can take on any value. And that's not true quantum mechanically. Okay? So quantum mechanics says these quantities are fundamentally discrete. How do you actually see this discrete nature? There are three elements to the recipe. One, the granularity will become apparent at the nanoscale. You have a capacitor. You can make any value of capacitance, roughly speaking, in the classical domain. If you make it small, there's only certain values that it will take. If you cool it down, then the thermal population will be so small that you can actually populate the ground state or some of these other levels. So you need to make it small, and you need to make it cold. Okay? And in particular, you need to isolate it from all the other nasty things around you so that these levels don't get mixed up. Okay? So those are the three recipes. It needs to be dark, cold, and small. Very lonely, and not talking to any of its neighbors. It doesn't sound very exciting, but mercifully, we're not qubits. So here's a circuit, very simple LC circuit with a resistor shunting it. This is a classical harmonic oscillator. Classically, all energies are allowed. Quantum mechanically, you know it's quantized with equal level spacing. I can adjust the parameters of the L and C with reasonable sizes to give me a level spacing in the 10 gigahertz regime. Okay. If I think about the resistance here, I have surfaces, I have interfaces, all of these things need to be made clean enough so that this resistance goes down. Okay. Moreover, I would like to have an anharmonicity in the level spacing, so I add a tunnel junction here. Adding the tunneling junction gives me a non-equally spaced energy level, so I can easily address any particular set of them. Okay? So here's a picture of a aluminum oxide tunnel junction that goes into this structure. Okay? What are other ways to relax your quantum superposition? Well, you can radiate the information away. Okay. So if the impedance of that circuit, unlike an atom, is close to 50 ohms or 377 ohms, it will happily leak its information out, and the lifetime will be very small. Okay. Moreover, even if you have wires connecting to it, they also have 50 ohm impedance. So you can't just directly add wires, and you can't directly put it in open space. An atom is very different because the impedance of an atom is high. Right? It doesn't couple to photons so easily. So it will not radiate away that information, and typically you don't put wires on atoms. They are weakly coupled. So this recipe is you take your little circuit, you put it in a cavity, a single mode cavity. This allows you to probe it with a microwave tone that comes in and reflects off of it. You can think of your qubit as a dielectric material that changes the frequency of your cavity. It's a very special dielectric because it only takes on two states. So if I look at the reflected signal from this qubit, this would be its reflected phase in one state or the other state. Okay? And there are more sophisticated optics like diagrams that tell us if I excite with an AC voltage, I just need to measure its in-phase or quadrature phase component to tell me the state of the qubit. Everybody okay with this? Raise your hand if we're roughly okay with this. Okay. If not, stop me. Interaction is perfectly allowed in the classical talk. So you put in a set of microwaves, right, at 10 gigahertz. You look at the microwaves that come back, and you look at the phase of the signal relative to your reference. If it goes forward, it's one state. If it goes backward, it's the other state. That's it. The challenge is you have to measure with 1 photon of excitation. This is not easy. Okay, but the concept is there. Okay, so this, if you like, for the experts, this is a homodyne measurement of 1 quadrature of the voltage. Okay, so we do need to amplify this signal because typically it's order of 1 photon, but luckily we've been in the amplifier business for a while. So we come up with devices that do this. This is generation 19 or 20 of parametric amplifiers. Yes?
So if the microwave reflectometer gives you the same phase, does that mean a superposition state?
Yes. Yes. And in fact, we believe the amplifier is also quantum. That's another talk altogether because there's no losses in it. So we amplify the signal. This is basically the size of this is 1 inch on one side. So we make these packages for the microwave. This is not the flavor of amplifier you have. There are different ones that are being circulated, but nonetheless, they're all based on similar principles. So what did we do with these amplifiers? So around 2010, 2011, one thing that was taken for granted in the atomic world is that you can measure an individual fluorescence event. You excite an atom, it relaxes a level, emits a photon, you measure the photon. For us, it emits a microwave photon, no way to measure that microwave photon. Okay. So we were able to go ahead and use these amplifiers to in fact count the individual fluorescent events. So that's real data from that experiment 2010, showing us that these amplifiers had good enough resolution to measure these fluorescence events. A little bit later, we thought, well, can you actually continuously track and with Bayesian updating, understand the trajectories associated with quantum evolution? So if you started with a superposition, as you were saying, can I actually make my best guess as to the path to an eigenstate? And this is also real data, showing you a single quantum trajectory. So the amplifiers were not only good enough to measure the state, they were good enough to give you near unity quantum efficiency to measure this. So this was still in the basic tools physics phase. Right? At this point, we have the recipe to make long-lived circuits. We have the recipe to measure them. That's still a long way away from actually building a computer. So life beyond single qubits. Well, first the fab has to get better, right? Because we need to have good control of all those parameters, make lots of them. So this is a snapshot of the clean room that's actually dedicated for my lab only on campus. It's a class 1 clean room actually in the end, where our e-beam writer is. And we're able to turn out 6-inch wafer of qubits in 2 days. And we have typically only a few % variation in all the parameters of these junctions and their frequencies. So that's pretty good. So that's a good starting point and very high yield. In this case, 99.4% over thousands of devices. Okay. But how do you design that device? Well, it becomes really tricky. Here's the basic LC circuit that's there. The junction is in between. These are the two capacitors. You have to balance your radiative loss. And you have to be very careful about how you actually add wires to the circuit. The adjacent modes can talk to each other and kill your coherence. The size of your bonding pad can kill your coherence. So typically my graduate students like to have a millimeter of bonding pad so they can hit it with the wire bonder. If you have 1 millimeter, you can see the crosstalk is unity in this chip. And no hope to run anything quantum. So those pads have to be at least 15 micrometers, so on and so forth. So many things that are not obvious and intuitive have to be taken into account in the design. Here's one version of the chip. It's about a year old. So there's 8 qubits here. 1, 2, 3, 4, 5, 6, 7, 8. They're connected in a ring. The lifetimes here are of order 60, 80, and now we have more than 100 microseconds. That starts to be good enough to actually run some kind of algorithm. Small, but nonetheless, starting to do something. What's the challenge here? A lot of surfaces. And let me show you, in fact, where these oxides may come in. One can do very fancy material science analysis, which we are also looking at, or one can use drops of water. So I must credit Kevin O'Brien, a former postdoc who is a professor now at MIT, said we should just use water droplets to study the surface. And he was referring later to this very old paper from 1974, saying that the angle that a water droplet wets on silicon dioxide depends on the monolayer thickness of silicon dioxide. Okay, so here's a chip from side view, and you can see how it's wetting the surface means I have silicon dioxide on the chip. Right, so we were able to find the particular step in the process where this was introduced, get rid of it with HF. You can see the droplet now, and you would see the T1 tripled. Right. So it's very subtle in terms of where these monolayers can grow and various interfaces and what have you. Moreover, I show you an interesting plot here. This is the coherence time, and we've sort of made an average, if you like, or made many measurements over a day, and they're broad histograms. So don't believe all the advertising. If you measured 50 microseconds today, it won't be 50 microseconds in 10 minutes. Okay? And the question is, what's the origin of these microscopic fluctuations? Your guess is as good as mine. So again, an outstanding challenge in the field. Okay. Moreover, one has to think about how to make more complicated things in 3D. Here are some pictures that can whet your appetite. You know, about how to bond chips together or build vias as they do in Lincoln Lab. Okay. The final piece of this is the amplifier you do have, Amir. We developed amplifiers with broad bandwidth to read out many qubits. It was us simultaneously reading out, I believe, 10 qubits with 99.5 fidelity. So that's another piece of the tool set to go ahead and read out many qubits. So the next part of the talk is starting to compute. So let me pause and take questions. This was meant to be a little bit of an introduction of the technology and challenges that are there. Any questions come up immediately? Please.
These junctions are not Josephson. They're just tunnel junctions?
These are Josephson junctions.
They are Josephson.
They are Josephson junctions.
So it's Josephson technology, and then you have a superstructure built on it as the detector.
That's right. That's the detector and couplers and all sorts of other computational tools. Yes.
You keep mentioning these amplifiers. Would you explain more about them?
I would like to. We're a little bit tough on time. But the thing to think about is basically a pendulum. So a pendulum, a physical pendulum, right, has a frequency which depends on amplitude, right, beyond the harmonic limit. And that's what we're doing with the Josephson junction, which also is an electrical pendulum. If you take it to the nonlinear limit, it becomes a parametric amplifier, where a very small change in the input changes its frequency. 30-second version. Okay. Starting to compute, two examples. One can think about examples in chemistry. This has become quite popular these days. This set of algorithms is not very demanding in terms of what's required, but it still has a lot of open questions. Then I'm going to show you a second example of how to look at the physics of black holes and information scrambling. That's a lot more challenging in terms of a simulation. Okay, the chemistry algorithm that people are looking at is something called a variational algorithm. It's half quantum, half classical. Okay? So it's a very clever idea, saying that my quantum circuit isn't good enough to run phase estimation. I can't run 1,000 gates. Right? The system is going to decay before that. But maybe I can break up the problem in chunks. You know, run a little quantum part, then you add some classical piece to it, run another little quantum part. And in particular, it targets the hardest part of the quantum problem. You know, where's the one slow step? Only tackle that one, quantum mechanically. So it's very clever. So what's the state of the art in chemistry calculations? Well, if you take an array of atoms, right, that have no particular symmetry, what's the largest array that you can analyze on a supercomputer? Somewhere between 50 and 100 qubits, or 50 and 100 atoms. And it turns out you simply run out of memory. Right? 2 to the n for a large number of non-symmetrical n is a big number. Right? And you would need petabytes of memory. And no matter which supercomputer you pick, you can't do anything beyond, let's say, 50 and 100. And probably will not do anything in the near future. So this nice graph produced some years ago by Martin Head Gordon says the number of atoms that can be tackled in a chemistry simulation depending on technique. So for the chemistry aficionados, this is a full CI. This is where you just solve the Schrodinger equation with all its bells and whistles. And you can solve 6 atoms. So it's not a lot, right? And this, it is a lot. It's a lot. It's a lot of work. But technologically speaking, it's not a lot of atoms, right? And it's pretty flat. It isn't getting better. These are all different approximation methods, of course. And you lose various elemental parts of the problem. So this is the thing we want to tackle. Why would you care? I'm actually, by the way, half a chemist. So when I was a chemist, we just mix stuff together and see what you get. When were we actually calculating anything? Well, there are many hard problems in chemistry that could really pay off. So for example, the Haber process. How many of you are familiar with the Haber process? Very historical process, right? For nitrogen fixation. Nitrogen, hydrogen, lots of temperature, lots of pressure. You get ammonia, 1 to 2%, roughly speaking, of all the energy resources on the planet. Okay? Well, you need to make fertilizer to feed the world. Important reaction. Legumes do it in the ground, 25 degrees, 1 atmosphere, but they make use of a catalyst that is very difficult to get a handle on. Party line, again, this is where the advertising kicks in, the salespersonship kicks in. If you had 100, 200 qubits, you could maybe solve this problem quantum mechanically. End of advertisement here. You understand what it means to have 200 good qubits, given the little discussion that we had, but nonetheless, it gives us a target. Right? It does give us a application to look forward. So how does the hybrid algorithm work? We come up with a cost function called h. And in this case, h may be the particular interspatial distance of a hydrogen molecule. Right? The energy will change depending on the distance. You can encode, if you like, the exchange coupling, J1 and J2. Right? So there's some cost that you want to minimize and find that structural solution. Okay? So the procedure is to map this cost function into some kind of qubit Hamiltonian, so you can vary its parameters. You prepare the state, so you take your arrangement of qubits, you create some state function psi. The parameters that you can enter as an experimentalist are written here as theta. Okay? So theta are all the knobs I can turn. Right? I can turn all the knobs theta, make some state psi. Then I measure psi. Right? I just measure the energy of psi. Okay? And then I go ahead and choose a new set of dials on my knob, and then repeat the process till I get the minimum energy. Okay? So basically you have a quantum black box. You can turn its knobs. You keep turning the knobs till you find the minimum of your cost function. That's it. Okay? The only quantum part is creating the state and measuring these correlations. Okay? Everything else can be done classically. You add it together, you do the minimization. All of this is some classical Nelder meter, whatever you want to use, algorithm. So, yes?
Any science behind the quantum part of it, or is it just random trial and error? You just keep tuning it on?
We would like to think there's science, but there is not. No, there is science. I'll show you what some of the tricks are. Okay. So here's actually the algorithm like we ran it. Okay. This is the Hamiltonian. You write it in terms of correlators, and that's where the quantum part happens. Right? You take two quantum objects, they know what the interaction energy is. You don't need to calculate that. You just read it off. Okay. And you run the series of gates to go through the parameter space, and you do the classical minimization, and voila, you get hydrogen. So this is actually computed on actual qubits. Okay. And in fact, the accuracy of the calculation is very good. It's within a millihartree. Okay. So it's good enough for actually making predictions. So this part was good. Here's the hard part. What if you go beyond hydrogen and have 10 or 20, so on and so forth? First of all, does the algorithm converge? Seems to converge quickly. Good. Okay. But what about the accuracy? How does it depend on the number of measurements you make? So we did this interesting experiment. To find the ground state is easy. That you just look for the minimum energy. To find the excited states, you actually do a Taylor expansion. So you go around the minimum and then find actually how the energy changes in different directions. And the number of terms in the Taylor expansion, if you each have more terms, the algorithm does better. So this may be a very interesting point. How does that resource scale with the number of atoms? Maybe you need to make a lot of measurements. Nobody really knows. Okay. So how do errors scale with system size? How difficult is it to prepare your initial guess? Is there some science to that? Maybe, but we don't know if it works. Okay. Is there a trade-off between accuracy and complexity? And then how do you define your quantum system actually being better if you end up making lots of classical measurements? So it's a very tricky slope in terms of benchmarking an algorithm and saying it's better than a classical one. But here's some of the physics issues that go into that. Okay. So this, if you like, is a very simplified quantum algorithm. It's not like Shor's algorithm or anything like this. Right? It's doing a very, very simplistic calculation. But you can even think about other questions. What is the effect of the variation of your coherence time on the quality of your algorithm? Remember I told you the times are varying. Here's a nice histogram of it. The nice thing is it seems to be somewhat insensitive to that. So we're making progress, answering how good this algorithm is. But it's still a road to go. Good. In the last part of the talk, I want to talk about black holes. Okay. This is a much more challenging experiment that we've been doing now for 2 years or so. It starts by acknowledging our collaboration. And I think some of the members are here, although I cannot immediately see them. Is Raphael Bousseau here? Good. He's there. So he has given us this beautiful slide of how, in a very geometric way, quantum information and quantum gravity are tied together. So there are a lot of things at the intersection of ADS, CFT, information scrambling, holographic principles, so on and so forth. So I will talk about one specific example of an experiment in progress. So let's imagine, first I want to thank our graduate student Marie Lou, who has hand-drawn all of the images that you'll see in the next few slides. You take some information, perhaps from Alice in Wonderland, you put it into a black hole, it gets very rapidly scrambled into the elements of the black hole. Okay. One can imagine looking at, let's say, the radiation that comes out of this black hole, which can be simply thought, because of folks here, as being another black hole connected by a wormhole. And the question is this information preserved at the output, or is it lost? Or is it irrevocably scrambled in some way? So here's a little bit of information. It goes into the black hole. It's immediately shared with the elements of the black hole, and it's radiated away. The twist on this experiment is that if you were to do the vanilla experiment and simply collect the radiation that comes off, you would have, according to Don Page, say roughly half of the black hole needing to be sampled to get enough information out. The trick here, put forward by Hayden and Preskill, is that if you already had a memory that was collecting this information, it would cause a rather instantaneous change in the memory. Right? So we have to come up with an experiment that actually scrambles, creates these EPR pairs to create the memory, and then look at what happens to the transport. Okay. So I'm going to twist it up on you a little bit. What about using three-level systems? After all, one need not only restrict oneself to 2 quantum levels. So we, in fact, use qubits in this experiment, 3 levels of logic. Okay? The experiment is proposed here by Benny Yoshida and Norm Yao. We start with an input state. We will come up with a unitary operator which mimics the scrambling of the black hole. Okay? After all, information is not destroyed, so a unitary is a reasonable model for this information scrambling. Then we're going to entangle with a memory, and that for us means making an EPR pair. Okay? And how do you know that information is preserved? We scramble and unscramble and compare the output with the input. Okay? And that tells us whether we are able to actually perform this scrambling operation and reverse it. Okay. So the goals here are not simply to produce something that can be perhaps done on a classical computer, but to test many ideas. First, we wanted to realize ternary logic. Can you actually compute with a physical system with 3 quantum levels and not 2? Moreover, can we actually create this scrambling U, and moreover, demonstrate that if you want to compare the input and output of this circuit, in particular, we can do a teleportation measurement. And this is a new tool in the toolbox. Because in condensed matter physics, disorder will also take away information. But how do you tell the disorder from your condensed matter physics system from the scrambling of your black hole? That's a hard problem. However, teleporting through this scrambler will in fact limit you to only look at that particular scrambling process. Okay, so we would wanted to demonstrate that in this experiment. Okay, so qubits in general can make a good use of resources because the number of elements in your Hilbert space scale as the number of levels to the power n. So if you have 3 to the n, you have a lot more levels for the same physical system. So you get a much more powerful quantum processor without doing a lot more work. Some important physics reasons as well. Okay, this plot here by Fred Chong shows that you can encode gates much more efficiently in qubits. That's basically this Hilbert space argument. 1 qubit is the minimal system to actually have a non-contextual classical description. So this starts to become a philosophically interesting object also, right, for looking at fundamental questions in quantum mechanics. And as we talked about, the minimal system to do scrambling is in fact 2 qubits. Right? And this experiment with the memory will require 5 qubits. Okay. So what does the scrambling unitary actually do? Every single qubit poly operator is mapped to a 2-body operator. So information which is in a single element of the poly group comes out as this sum, graphically shown here. So here's the identity on 1 qubit, a certain poly operator here, and this gets mixed up into a sum of polys. Okay, so one example of scrambling is what's called the Clifford scrambler. So that operator is shown here. I start off with a group with I and j, and I permutate the axes such that z goes into this particular operator here, z here, and z squared, so on and so forth. Okay, and this is a perfectly self-contained way of describing a system that's undergoing scrambling. It's not the only way, but this is a way to do this. Okay. Oops. Okay, so let me take you through the experiment and the pieces that go into it. The first thing I have to show you is that these systems go beyond simple physics experiments. Right? I need to go ahead and build the states, do rotations, measure them, do tomography. So I'm going to walk us through this. Stop me if some part requires some more explanation. I won't be able to go into all the details of this given the time that we have. But you'll see the Manhattan plots and pictures. Okay, so the first thing I need to do is let's demonstrate that I can control 2 levels in the qubit. So if I have 2 levels, the basic operation is a rotation. Okay? So I need to be able to rotate arbitrarily each qubit and measure it. The rotation in 2 space is basically generated by the polymatrices that are shown here. So I have gates which look like polymatrices. And in this particular case, I can oscillate between 0 and 1, say. These are called Rabi oscillations. And if I prepare a superposition state, here's the output tomography which I made with my measurement. So you can see it works. I create the 0 plus 1 and it has elements at the right spots. So that's experimental data, showing you that I can control a 2-level system. Here's the picture of the chip. Now I have to introduce a gate. right? How do you get logic operations between two neighboring qubits? This is hard in the field because quantum mechanics, if you leave it on all the time, it's too much interaction. If you leave it off, it takes too long to do the gate, right? So that makes it a hard problem. So we do something called the cross-resonance gate. So I will try to illustrate this with both of my arms because I need two of them for 2 qubits. Okay, here's a qubit, it rotates. Here's a qubit, it also rotates, right? Let's imagine this one rotates at a different frequency than this one. I'm trying. Okay, and then you need to get them to couple to each other. So here's a nice trick. This has a certain natural frequency. I move this one at the frequency of this one. I force it. It doesn't move a lot, but since it's at this frequency, any weak coupling will cause both of them to rotate together. So it's a forced pendulum that rotates at the frequency of its neighbor. And that's called the cross-resonance gate. Okay? So you'll see that in the literature. Drive one pendulum at the frequency of its neighbor, and you'll couple them. If you like level diagrams, right? Here's one qubit, 0. Here's the other qubit, 1. This is driving this qubit in this axis, so I drive the 0 to 1, 0 to 1. If I drive the other qubit, you see 0 goes to 1, 0 goes to 1. Without any coupling, I can't drive them independently. However, with a small weak coupling, you see they get hybridized, and I can drive one at the frequency of the other. Okay? And it depends on the detuning of the 2 qubits. When the 2 oscillators are close in frequency, they will work together much more rapidly. So that's the principle of this gate. Okay? For the fidelity aficionados, here's a very rough tuning of the gate to give you 98.5% fidelity with nothing special done on the gate. Okay? So ternary logic. Here are the 3 levels now. I can access all of them. I can Rabi flop any pair. I can check the quality of my rotations on each 0 to 1 or 1 to 2 to 1 part, a few parts in 10 to the minus 4. So, okay. How do I do the rotations in 3 space? Well, there's a nice trick by Murray Gell-Mann. You don't use the Pauli matrices, you use Gell-Mann matrices. So these are the generalization of rotations in 3 dimensions. Okay. So you need to pick a subset of these matrices that can be used, and some of them are quite nice. If you look at lambda 1, lambda 2, 4, and 5, you see they have zeros along certain rows and columns. So this is basically using the same logic as you would on a 2-level rotation in a 3-level system. So that's pretty easy to implement. Some of these are harder, of course, where you mix all of them together. Okay? And then if you adjust the phase of your microwave field, you can get these 2 as well. Okay? So that's the set of gates that you can now use to manipulate your 3-level system. Okay? And you have a new family of logic gates. This is why this experiment took us a while. We have to redefine the gate set for all of these operations. Okay. The cross-resonance gate works by different Rabi frequencies depending on your control system. Okay, so we pick a place where you can tell the 2 apart. Similar thing applies with 3. You can pick a place where a detuning, if you like, where you can have a controlled NOT operation. Okay. So here's actually the gate. If I have one of my qubits in 0, or in state 0, this is the frequency of Rabi oscillation. If I put it to state 1, this is the frequency of Rabi oscillation. And in this case, I've chosen it so that if it was in the 3rd level, I get the same as the first one. Okay? So that's the logic family that I've chosen. And it works pretty well. Okay. So can you create the entanglement? Can you create the quantum memory? I start off with the state with equal population in both. I apply rotations to spread the love around in this density matrix. Okay? And in the end, I can prepare this EPR state 0, 0 plus 1, 1 plus 2, 2 with equal proportion, and that's the actual data for the output. So that's an entangled EPR pair of qubits, okay, with 94% fidelity. Okay. Then the scrambler. The scrambler gate in pictures, what it does is it spreads information, okay, along the diagonal, if you like, of the density matrix. It doesn't like information in one qubit or the other. So it's a set of swaps that maximally spreads out information. We can decompose it into a set of C0 gates that are here. And the first time we ran it, we couldn't go to Raphael with this number. He would laugh at us. It only has 52% fidelity. And that's because it has a lot of gates to actually get it done. Moreover, your system is like a dipole. The dipole coupling is always on. Right? So you have to use dynamical decoupling and other things you borrow from solid-state physics to turn that off. Then you need to also cancel the crosstalk. And in the end, you end up with a pulse sequence that I can't fit on a page. This is the actual pulse sequence for the experiment. These are the pulses for the 2-qubit gates, the EF transition pulses, the GE pulses, starting from here, going to here, which is 5.7 microseconds worth of pulses. Okay. You have about 60 or 100 pulses. It's not a small algorithm to execute. But we are able to do it now. And if you look at the output, okay, I put in a certain poly state at the input, and I look at the output. If I have a single qubit gate, all the information is contained within that qubit. Okay? So here's the actual experiment. A local gate, indeed. This is the theory, this is the experiment. You see all the information is in the 1 qubit subspace. You run a 2 qubit gate, you create selective entanglement. Okay? And you run scrambling, this is actually the output. So the gate actually is scrambling now with a reasonable fidelity of about 78%. These are all the possible combinations that you can scramble. It doesn't scale. Right? There's 81 elements to do your tomography, and it takes 1.5 hours just with a few qubits. If you had 20 qubits, it's impossible. So then you look at teleportation to see if you can really see the physics that we're looking for. Here are all the pieces for your teleportation. You put state in, create the EPR pair, look at the output, and it works. Okay. So here's the input state, and you look at the output, and indeed, you start to see some fidelity at the end. Whatever you put in does actually come out at the end. This plot, I think, is overselling it. This is much more reasonable, saying that how good is your teleportation? One should compare to a limit. So there is a very classical limit of 33%. Right? That's if you just randomly measure 1/3 of the time, you should see some correlation of your output relative to your input. We can beat that limit. We're roughly at 42, actually 48% as of this morning. So we can beat that limit. However, it would be nice to beat 50%, in which case there would be no hidden variable or some other theory that would kind of bound you and put a little loophole in your protocol. So that's our goal, to get beyond this 50% limit. We'll get there. But again, there's 100 pulses, a lot of gates in that sequence. We're playing around with how to compile it better and so on and so forth. Okay. Future direction in this high energy physics domain, it would be nice to try to look at this Ryu-Takayanagi formula, and in particular to look at the scaling of entanglement entropy and see if there's a real deep connection here between these condensed matter systems and high energy physics systems. Moreover, I did talk about black holes in this very discrete variable way, and there is a good mapping for it, but it would be nice to have continuous variable that you can scramble. So we are looking at that. Okay. Finally, to end with, we are now in the business of trying to put together a large tool where we can bring all of these pieces of the puzzle together in a very interactive fashion. Okay, and that's called the Advanced Quantum Testbed. We have a building dedicated for this now at LBL. So that will be commissioned in about a year's time. Okay. Here's, for example, a snapshot of this large XLD 1000 fridge, which will come online in a few months. The diameter of this cold stage, which is at 7 millikelvin, is 1 meter. Okay, so just to give you a sense of scale of what's there. And it has different pockets for different processors, which will be run at the same time. Okay. Science that goes there starts from foundations, as we talked about, to algorithms, materials, and in particular, the engineering needed to put it all together. Okay. So I want to end with more questions than I've answered. One can start to think about how do we stabilize quantum coherence in an open many-body system, right? And what does physics look like? What does physics look like at the edge of the complexity frontier? That's really, I think, the physics question that drives many of us. In particular, can we efficiently sample information from such a many-body system? Can we conceive of machines to treat data fully quantum mechanically? I didn't talk about the engineering challenge of actually trying to process quantum data. Okay. How do we parameterize, verify, validate the information capacity of a quantum system? How do you know your computer is actually good enough for the task that it wants to do? And what role does entanglement really play in these computations? And how do we express any advantage in some platform-independent way that tells us really the interplay between classical limits and quantum foundations in this particular landscape? So at 25 past the hour, I stop here, and thank you for your attention.
I think we have time for questions, actually.
So if you know your single qubit coherence times,
Right.
and then you go to a multi-qubit system that you want to make maximally entangled, is there a simple relation of the coherence times for those complex states
Right.
to the single qubits?
So the question is, let's imagine I have a single qubit, an isolated element that has a certain lifetime, and then I want to actually go ahead and put lots of them on a chip. So the first level of question there is, let's imagine I don't couple them, right? I just plop down atoms. We are able at this point to maintain the coherence time for, let's say, of order 20. No problem. We haven't done more in the third dimension, but in 2D we don't have a problem. The challenge comes in when you try to couple them in some way and still have the same lifetimes. And it's really an electromagnetic challenge where we have to get better at HFSS, and we are getting better at making sure that all sorts of odd modes that can develop and cause decoherence are not entering the problem. So I don't see an immediate fundamental limit to sort of maintaining coherence just on the chip level. There's a second part of your question, which is, what if I make a state that's more complicated? I make a GHZ state or a Noon state in optics and so on and so forth, or a Schrödinger-Cat state. Those states are subject to the theoretical norms that we have. If you have a cat state and you lose a photon, it will be that sensitive to it. Right? So I think there's no easy way out of that. We will need topology to do better than that. So I think the statement at the end of the day is none of the qubits that you've seen here today will form a quantum computer. I bet money on that. Right? Because if you need to get hundreds of thousands of qubits, we need a different recipe, right? To think about fault tolerance and to think about information encoding. But we can still answer interesting physics questions along the way.
That lab is very interesting that you just did the last slide where you I think
Yeah.
some hard work. All right, I have two questions. When you finally get this thing done, do you have in mind a first application that will showcase it and say, look what we did with this? One that's your favorite. Okay, and the second part of the question is, how much does this thing cost?
Cost, amongst friends, what's the cost?
Well, I mean, just general numbers, like to get an idea.
This is, for me, fridge number 8. Okay, so I have 7 fridges already in my lab. A fridge bare is $500,000. A fridge like this is $1.5 million when you put everything on top of it. It costs much less than FTEs at a national lab, right, over a few years. So the hardware cost is not debilitating. The cost of people is quite expensive, and the number of people that you need to get it going. The project that I showed you, the AQT, is at this moment a $60 million project, right? So that's where we're at with this one, not including the cost of renovating a building and so on and so forth. So that gives you a sense of the scale. What I would like to do is, in the beginning stages, I would like to see the ability to manipulate, right, a set of quantum states, okay, that are in the number of, let's say, 50 to 100, right? Not even running an algorithm. The fact that you can create a superposition state of 50 elements in some highly entangled way is quite a serious endeavor. And to come up with the tools to just verify that you actually have this entanglement, I would be quite happy with that, right? And it's a challenging task. On the surface, it seems very simple and mundane, but it tells me that quantum mechanics exists at 100 entangled elements. Right. And the question is, what does that look like? How does it relax? You know, what is that animal? Would be, I think, for me, the first and perhaps quite a lofty task. Because to be honest, I'm not sure which of these applications, we don't know the best application for quantum yet. We are in the early days, like for computing. There were many military applications, but that didn't drive your iPhone till many generations. So neither do we have the right technology to bring quantum into the mainstream, nor do we have the killer app that will do it. But we do have now the window to a new technology. So just to see it work is perhaps good for me.
Can I follow up on that, please? Just the title of your talk is the Great New Tomorrow.
Yes.
And I'm still massively confused about what this window is. So you have sensing technology for Josephson qubits, and you're making more complicated versions of them, but it's basically a more complicated version of them. And so I think what's left to do is scale up and control errors. So where are we at with scaling up and controlling errors?
That's a hard question, because the ways that we know how to scale errors aren't the ways that I'd like to control and scale errors. Right? So the question, so there's the fundamental physics question. And maybe we will learn from the high-energy physicists. Human beings put things in square lattices, and that's a very heavy way in the surface code to actually try to encode and scale for errors. If we go with that error correction paradigm, which is common now, you will need thousands of qubits for each one logical bit. And I don't believe that, period. However, if you arrange things in tensor networks or things that have some holographic nature to it, life can be much more friendly. So I think it's even more challenging. We don't know how to actually put in the right error correction scheme. So for me, Bob, I would think that creating an n-body quantum state and looking at its correlations and looking at its stability is a tremendously interesting problem. Now, what algorithms you want to run with that, this will change with time. If you build it, they will come. Okay. I think there was a hand up here somewhere. Yes.
Can you comment at all on how you see the role of industry in this whole process? It seems
Good.
like a hot topic there as well.
That's absolutely right. So we are rather complementary to industry. Right? We would like to understand what the challenging physics questions are and eliminate those pathways which will produce a product. And I think that's really what this test bed is about. Let's figure out the right error correction schemes. Let's figure out the right connectivity that you need to stabilize quantum mechanics without having to do that in industrial platform. So there will be a tight coupling between us. And in fact, the image that I showed you, we didn't actually produce this. We have wired up many fridges. We actually contracted out to Bleximo, which is a company that's on LBL soil at the moment. It is a spin-off from Rigetti. So they are, in fact, very good at designing cryo packaging. So they've designed all of it. Right? So the idea there is there are many places where we can sort of go ahead and lift this together with industry where it makes sense. I think there was also one more hand.
Can you comment a little bit about machine learning and quantum computing? Is this all hype or is it real?
Oh, only in that binary basis, or can I add more words? It is a combination of hype and real. It is a combination. I wish I had time to talk about this subject so in the slides, but let me comment on it now. There are two flavors that you can think about this. There is classical machine learning for quantum data. Right? And we are in fact using recurrent neural networks to process a lot of the data here. And it's very interesting to see if these types of methods can do better than a master equation, say, at learning quantum dynamics. And in particular, can they learn about model-independent ways where the Markov approximation doesn't work? So there may be really good applications of classical machine learning in quantum problems that are not easily solved in the usual mechanisms that we have. Okay. So that's a big data problem. Then the other question is, can you actually make classical machine learning go in a more efficient way by using some quantum part? So typically those algorithms will have some kind of matrix inversion step. So there's the algorithm that I flashed, the HHL algorithm. If you can make that work, it will make machine learning go better. However, to make HHL run is a heavy task. Okay, so that's the tricky part of this. The third flavor is machine learning, which is a quantum algorithm for quantum data. So this is really, I think, exciting. But I don't know at all how to do this. Right? But it involves not going into to a classical intermediary. Right? I have some data coming out of my qubits. I have some quantum machine learning step, and it gives me another optimization. That, I think, is very interesting, right? And may not be subject to all the roadblocks and speed bumps that this classical quantum conversion may have. Does that, Steve, get to three flavors of this machine learning?
I was thinking more of the last one.
This one is tough. I think that's rather developmental. I don't personally know of very good pathways for doing that. But I think it's got to happen. To deal with this quantum data, if you keep converting it to classical, we run into a problem. There was another hand here.
Does zero-point radiation cause any decoherence in these systems?
So there is indeed zero-point motion, but it will not couple to, it will not take energy out of the system.
Not energy out, but does it affect entanglement?
If you just have two, this is a very interesting question. If you take two qubits, right, and just couple them, there is something called entanglement genesis. Every once in a while, you can actually generate entanglement by fluctuations. But this is all controllable with us because typically the probability of that is very small. And moreover, we drive very rapid transitions to actually go ahead and turn it on. In the same way that if you put two atoms together and you want to make a molecule or what have you, you are able to control that much faster than anything else. And there are, of course, thermodynamics arguments about the Gillard engine and what you can actually get out of this. So in the end, you'll never get work out of it. But you could, in fact, have the sun, moon, and stars line up to create entanglement. We are using electronic excitations, right? And in fact, there's no single electron. It's a many-body state of this oscillator that's there. It's a charged state of an island. So this is true. We are using electronic states and not photons. The photons come in to interact with that electronic state for measurement.
Coherence and photons more noise, different form of noise, but photons less.
So the quantum mechanics is a great theory. There's no free lunch. Right? If you hide your system in a photonic degree of freedom that doesn't couple to anything else, it will not decohere, but you will also not talk to it. So there's always this challenge of how do you actually talk to something quickly and get information out. So by the way, I didn't comment on that slide that had all the different technology platforms. In my mind, it's actually a little bit of a lackluster reason why these circuits are very good. They're not difficult in any one dimension. Right? There's no real fundamental stoppage. You just need to improve all of those parameters a little bit. If you start with a pure photonic system, it doesn't talk to anything. Right? If you talk to something that's the size of a single electron, it talks to everything. And these things are somewhere in the middle. Right? So it's no real fundamental reason that nature allows you to engineer this. They're big enough that you put your hands on it. They're decoupled enough that you can manipulate them. So that's not a super exciting takeaway for our field, but it is true. Yes?
I don't understand the basics. If you have a Josephson junction, you could model that with a nonlinear inductor. Mm-hmm. And so long ago there were nonlinear ferrites to make paramps.
Yes.
But paramps naturally would make pairs of two that are entangled.
Yep.
You could put many of them into that box, but so what I'm missing is how do we go from many pairs of two to the more massive entanglement that of course in this class.
Yep. So a Josephson junction has a current that goes across. The magnitude of this current, I naught, sets the height of your potential, which is a cosine potential. In the limit that you're talking about, it's a high potential, so you don't feel the level quantization. And then you produce lots of levels. If you make this I naught less than 1 microamp, then you will have only a few levels. So that's the limit of the qubit. So you simply have always a cosine potential well. If I shrink the height of the potential well, it's like having a particle in a box, but in a cosine box. So small junctions have quantized levels, big junctions have many levels, are this classical.
So if I just take a nonlinear inductor and linear circuit and join, I don't know whether you need capacitors or not, but that's not going to work from what I think I hear you saying.
It would perhaps not work because of two reasons. One, you may have too many levels, and the resistance, right? So you need to get rid of all the dissipation. So the only thing about this Josephson junction, you're absolutely right, is the only reactive element I know how to make non-dissipative. If I could make a capacitor nonlinear, non-dissipative, we have another family of qubits. So there's weird asymmetry in the world that somehow it's this one nonlinear inductor that we know how to tame.
So I think we should end the session. Let's thank